number 38 on page 219. There is a set S with three vectors in R4. We want to show that the set is linearly dependent, and by finding a non-trivial linear combination whose sum is a zero vector. Okay, so this is the idea. Let me write the vectors here for you. Okay. Well, remember how we showed that vectors are linearly independent or dependent. We set a linear combination to be equal to the zero vector, and when we solve this, if the solution for the C's is just a trivial solution, then we say that these vectors are linearly independent. But the exercise is already telling us that they're not. Okay, they're not linearly independent. They are linearly dependent. Therefore, when we solve for these C's, we're going to find a solution that is not trivial. In other words, some of these C's may be different than zero. Maybe all of them are different than zero. Maybe some of them are different than zero. In any case, at least one of them will be different than zero. Okay. Now the zero vector here is, of course, 0, 0, 0, 0. Okay. All right. Let's set up the matrix. I want to show you another way of constructing the matrix. Okay. Another way to show why these coordinates will be vertically, will be in columns. Okay. Remember, be careful with that, because in some cases we don't know if they're going to be in columns, especially if they're not vectors like in R3 or R4. We can see an example of that later. But here is another way of looking at these as vertical. This is C1 times the first vector, so I can write C1 times 1, 2, 3, 4. Okay, that's another way to construct a matrix. I don't know why I wrote C4. C2, 1, 0, 1, 2, plus C3, 1, 4, 5, 6, and that's equal to 0, 0, 0. Okay, and then, well, you can see that this is just a matrix with all those vectors in columns. Okay, here it is. Now I think this would be easier to understand because it comes straight from matrix multiplication, right? How do we multiply matrices? It's always rows times columns, right? So you can see here that when you multiply rows times columns, this one gets multiplied to C1, and then plus this number 1 gets multiplied to C2, and then plus this 1 gets multiplied to C3 here. Okay, same thing with the second row. The second row is 2, 0, 4. It gets multiplied to C1, C2, C3, right? So it's always row times column. That's another way of obtaining the matrix. And of course, this leads to the augmented matrix like that. Now let's solve. You're solving for C1, C2, C3. 3 variables, and we have 4 equations. Let's see what happens when we reduce that. When reduce echelon form. Okay, here's the matrix, and I put that in the calculator. Let's reduce it, and here it is. Okay, here's the reduced form. I'm not sure if you can see this, so I wrote that in here a little bigger. Okay, what is the conclusion here? Well, the first conclusion is, from the first row, is that C1 plus 2C3 equals to 0. Okay, that's the first equation there. So in other words, C1 is negative 2C3. Well, let's look at the second row. Second row says that C2 minus C3 equals to 0. Well, that means that C2 is C3. Okay. Look at the third row. All zeros, that means there's no restriction, there's no impossibility, everything is fine. There's no 0 equals to 1 or 5 equals to 7, none of that. So the third row implies that C3 can be any real number. And the last row doesn't mean anything. We don't have C4. Okay, we don't have 4 variable there. It doesn't mean anything. You just ignore it. Okay. Well, now here it is. Is this trivial solution? No, because the C's can, some of the C's could be different than 0. Like if I pick C3 equals to 1, then C2 would be 1, and C1 would be negative 2. Okay, so there are a bunch of solutions. There are infinitely many solutions. So if I pick C3 equals to 1, then C2 would be equals to 1 as well, and C1 equals to negative 2. Well, if you don't like that one, then you can pick another one. Here's another one. C3 equals to 5, and C2 would be 5, and C1 would be negative 10. Okay? Alright, that shows... Okay, let's look at the big picture. What is the big picture here? Remember, we were trying to find these C's, and if these C's were... the solution was a trivial solution, then these vectors here would be linearly independent. But it's not the trivial solution, and you can find here some of them are not 0. This one is not 0. So we can write one as a linear combination of the other. Let's say that. Okay. So this means that linear combination, negative 10 times the first vector. The first vector was 1, 2, 3, 4. Plus C2 was 5 times the second vector. Second vector was 1, 0, 1, 2. And then plus the third vector, C3 times the third vector, which is 1, 4, 5, 6. And this was equal to 0, 0, 0, 0. Okay? And see, that's linear combination of the vectors equal to 0. It's non-trivial. Let's see, what was the question here? Show that a set is linearly dependent by finding a non-trivial linear combination. Here's the non-trivial linear combination. Then express one of the vectors in the set as a linear combination of the other vectors in the set. Well, that's easy. You can pick any of these vectors here and solve for it. Like here, if I pick 1, 2, 3, 4 equals, then I move these two over to the other side, right? And divide by negative 10, right? So it will be negative 5 over negative 10, 1, 0, 1, 2, and then minus 5 over negative 10. Right, move this over to the other side. The other side is just a 0 vector, so I can throw the 0 vector away. It doesn't influence anything. 1, 4, 5, 6. Here it is. Right. The first vector is 1/2 of the second vector plus 1/2 of the third vector. Okay. And that's the end of it.